Hello, it's another A-Level Further Maths video here on the Core Pure Mathematics Book 1 material. We're finishing off Chapter 1 complex numbers in this video, and we're going to be looking at extending some of the ideas we did in the previous video to solve cubic and quartic equations. So let's start off by seeing how much you remember about the factor theorem and doing some factorizations. Here I've got a cubic function. I'd like you to pause the video, use the factor theorem to show that z minus 2 is a factor of this, and then do the factorizing. Okay, so do you remember how the factor theorem works here? Let's go through this together. So if z minus 2 is a factor, then it means that if I substitute the value of 2 into the function, I should get the answer 0. And if I do get the answer 0, that proves that z minus 2 must be a factor. So let's quickly work this out. So substituting 2 into it, we end up with 2 cubed minus 8 lots of 2 squared plus 22 times 2 minus 20. And if you work out what those are, you should end up with this one here becomes 32. We have a 44 here. That minus 20 is still hanging around. And that does indeed become 0. So z minus 2 is a factor. Okay, so there's our factor theorem. Let me just try and arrange that on the screen so you can see it. Okay, there we go. So then we have to factorize it so we get that z minus 2 factor out. There's a couple of ways of doing this. Now I'm going to go through the method which I think the textbook uses, which is to do it doing algebraic division. So let's set it out a bit like this. So this is how I set it out. Excuse me. If you had a different method of doing this and you factorize it a different way, then of course that's fine, provided you end up with the same answer at the end of it. But I'm going to go through this method just to remind you how this method works, because this is the method I tend to use when I'm doing it myself. Okay, so let's give myself a bit more space up here. Right, so I need to multiply z by z squared to get z cubed here. And if I multiply the other term by z squared as well, I end up with minus 2 z squared here, and I have to subtract that away. Hopefully you're familiar with the method I'm using here. Okay, if we do minus 8 minus the negative 2 there, we end up with minus 6 lots of z squared. Bring down the 22z and do it again. Z times what gives me minus 6z squared? Well, that is minus 6z. Let's do that again. So z times minus 6z is minus 6z squared. Minus 2 times minus 6z is plus 12z, and subtract that away. And we end up there with just 10z. Bring down the minus 20 and do it one more time. Z times 10 gives me 10z. And then if I have minus 2 times 10, that's minus 20. Subtract that away. And we do end up there with a 0 remainder, which is exactly what we want. So all that must mean that the thing we've got up here, the z squared minus 6z plus 10, must be the other factor. And so our f of z here must equal z minus 2 times z squared minus 6z plus 10. So hopefully you remember and you're familiar with that process there. Now, why are we reminding ourselves about this? Well, it's going to help us because we're going to need to do this sort of thing when we are solving these kind of cubic equations, and maybe even higher level polynomial equations like quartics as well. So what we're going to do is we're going to use this idea to solve where the same function, so this is the same function we've just been dealing with, the equation where that function equals 0. Okay, so that factorizing work we've done already here is going to be useful for us here, because if I wanted to solve where z cubed minus 8z squared plus 22z minus 20 equals 0, the first thing I might want to do is actually factorize it, because when we factorize things when they equal 0, then that makes things a lot easier. So this is what we've already done here. We've already done the work and we factorized it to look like this. Now, why have we done this? Why is this useful? Well, I'm sure that you remember that when we have this kind of thing, two factors here multiplying together to make 0, then we're going to get solutions either when that first factor equals 0, which obviously means that in this particular case z would have to equal 2. So there's one solution of our equation. But also we're going to get solutions when this second factor equals 0 here. Now, this happens to give us some complex roots in this particular case. Now, I'm not going to go through the details. I hope that you're familiar with this by now. But if I use the quadratic formula, it turns out that I end up with z values here of 3 plus or minus I. So to solve that equation, the first thing I would need to do would be factorizing, and then solving whatever I end up with each bracket here like this. Okay, make sure that you have another look at that if you need to, because right now I'm going to ask you to do one yourself. Here's another cubic equation, or another cubic function, and I'd like you to do some factorizing first, and then with that factorized version, solve the equation. Off you go. How did you get on with this one? Well, let's write down the answer you should have got here. Our f of z, when we factorize it, we're given a bit of a clue there. We're told that z minus 1 is a factor. But when you factorized it using whichever method you like, you could have done long division, you could have done some other method, you should have ended up with 2z squared minus 2z plus 13 as the other factor. So, hopefully you got that right. If you did, then let's keep going, because what we now need to do is we need to solve the equation where these two things multiplied together gives us the answer 0. Okay, so we either get z minus 1 equals 0, which obviously gives us z equals 1, or we get the 2z squared minus 2z plus 13 equals 0, and that happens to lead to z equals a half plus or minus 5 over 2i. Did you get it right? Now I just want to make a quick observation here. We've solved two equations here, two cubic equations. Both of them happen to have one real root and some complex roots here. But notice that the complex roots have occurred in conjugate pairs. Okay, so any complex root that there was of these equations, it just so happened that its conjugate was also a root. And if you think about it, based on what we did in the previous video, that must be always true, right? Because when we factorize, if we factorize down to a quadratic factor, then we saw in the last video that when that equals 0, if it's complex, those complex roots must appear in conjugate pairs. And this is quite a useful and important fact. Now I've put a few things on the screen here. So you'll see here that one of the things that we notice about the degree or the highest power of the polynomial that we end up with here is the number of roots we get is equal to that degree of the polynomial. So if we have quadratic equations like we did in the previous video, we always had 2 roots. If we have cubic equations like we've looked at so far, we've ended up with 3 roots. Quartic equations, it won't surprise you to learn, we'll end up with 4 roots, and we'll have a look at one of those shortly. But also at the bottom of the screen, just what I was saying just a few seconds ago, that if we have real coefficients in our polynomial equation, if there are any complex roots, then those roots must occur in conjugate pairs. And that is a very, very useful fact for us, which we should be very, very well aware of. Please do make sure that you fully understand what's on this slide before we move on, please. So pause the video and think about it if you need to. Okay, right, let's up the stakes a little bit here. Let's take all of that knowledge we've just got here and try and solve a quartic equation. So this is an equation with the highest power of the x here in this case is 4. So we're going to see if we can do this one together. Alright, so we've got our equation here that we're trying to solve. So it is x to the power 4 minus 6x cubed plus 38x squared minus 94x plus 221 equals 0. And we've been told that 2 plus 3i is a root of this equation. So we've given that root. Now this is a complex root, so we should be able to immediately write down what one other root of the equation is. Have a think about it. Okay, so it should be that you were thinking of the conjugate. 2 minus 3i is also a root of this equation. So how are we going to make use of this information? Well, what we're going to try and do is we're going to try and sort of construct the factorized version of this by using this information here to give us one of the factors. So if you remember back from the previous video, we can construct a quadratic equation with these roots by recognizing that the sum of the roots is going to be the negative of the x coefficient, and the product of the roots is going to be the constant term. So let's do that here. Now if I add together these two roots that I know, I'm going to end up with 4. And if I multiply them together, I'm going to end up with 13. If you need to stop the video and work that through yourself to check that, please do. However, I'm just going to keep going with this, and so that tells us that we could construct ourselves a quadratic equation where x squared, remember it's the negative of this and the positive of this are the numbers we need to put into our equation as our coefficients. So it means that that equation there would have the roots given by these two numbers here. Okay, so how is this going to help us with our quartic equation? Well, what it must mean is it must mean that I can factorize it into x squared minus 4x plus 13 times some other factor here. And if I can work out what that other factor is, then I can then work out the roots of the equation by working out whether other factor equals 0. So what goes in there? How am I going to get that? Well, what I'm going to do is I'm going to do a bit of long division here. Okay, so let's see if we can sort out our long division. Now, you may not have done one with a quadratic divisor here, but it works in pretty much the same way. So I will go through it. I'll do it quite quickly, but we'll go through this. So the x squared times another x squared gives us x to the 4. Multiply the other terms by x squared. I think we end up with minus 4x cubed here and plus 13x squared here. Subtract that away, and let's see what we've got. Well, we're going to end up with minus 6x cubed minus a minus 4x cubed becomes minus 2x cubed. And then 38x squared minus 13x squared is 25x squared. Bring down the next term, do it again. So x squared times minus 2x gives me the minus 2x cubed. Let's just put that up so make sure that you can see what's going to happen. Then I think we end up with minus 4x times minus 2x, which is plus 8x squared. The next term here, the 13 times the minus 2x is minus 26x. Subtract it away, and let's see what we end up with here. I think these terms become 0, then we end up with 17x squared, and I think that's minus 68x here. Bring down the plus 221. And let's just quickly finish this off. So I think we need x squared times 17 gives me what I need here. So the minus 4x times the 17 is minus 68x. This is all working out nicely. 13 times 17, well, I'm pretty sure that's 221. Subtract that away, and you can see that we've ended up with 0 here. Okay, so with all that in mind, this was the bit we're really interested in, right? So we can now write that we've got x squared minus 4x plus 13 times x squared minus 2x plus 17 equals 0. So just pull that up there so you can see. Remember, that's the first factor we already knew, and then we've now got this other factor here. So that's where these two things come from right here. Okay, nearly there now. So if we now solve where x squared minus 4x plus 13 equals 0, well, that's the one we already knew because that was the one where we got all this from. So that means that we end up with x equals 2 plus 3i, or x equals 2 minus 3i. If we solve this one, turns out this one also has complex roots, and I'll just jump to the answer here. We should end up here with x equals 1 plus 4i and x equals 1 minus 4i. You can check that by solving that quadratic equation yourself using the formula, and you should end up with that as the answer there. Okay, there was quite a lot going on there, quite a long process in many ways, but see if you can have a go at one yourself. If you need to go back and re-watch that, then obviously please do, but when you're ready, have a go at the question on the screen, and I'll come up with the answer in a few seconds. So pause the video and have a go at it first, please. All right, how did you get on with this one then? So here's just the answers. So you should have ended up with, we knew that 1 plus 2i was a root already. So that tells us straight away that 1 minus 2i must also be a root of the equation. And if you do the factorising, you should end up with, when you factorised it, you should have ended up with z squared minus 2z plus 5 multiplied by z squared plus z minus 12. So this one here leads to those two roots that we already knew. This one here actually leads to two real roots in this particular case. Z equals 3 and z equals negative 4 is the solution you should have ended up with there. And there we are at the end of the video. So hopefully that all made sense. It brings together some ideas from your regular A-level work, things to do with the factor theorem and algebraic division possibly, together with this idea of finding roots of polynomial equations and quadratic equations from the previous video as well. More practice questions in exercise 1F. They get slightly tougher in that exercise, so I do strongly recommend that you work your way through as many of those as you can. But that's the end of chapter 1. In chapter 2 we are going to look at complex numbers a bit more, so make sure that you are as good as you can possibly be before we get on to those. Okay?